We're surrounded by electricity every single day, but the way it actually works is one of the most misunderstood ideas in all of physics. So today, we're going to completely challenge what you think you know about something as simple as current flowing through a wire. Turns out, the reality is way stranger and honestly a lot more elegant than you might think.
So think back to science class. You were probably taught that a battery is basically a pump, right? It just pushes electrons down a wire like water through a pipe. It's a simple, clean analogy that works just fine for basic circuits. But, and this is a big but, when we really look closely, that entire model just falls apart, and it reveals some absolutely fascinating paradoxes.
So this is the story we all know and love. The battery creates an electric field that runs along the wire, and this field is the push that gets all the electrons moving. It seems totally straightforward, but this very idea, this simple push, leads to a huge contradiction that took physicists a while to sort out. And that brings us to our first big mystery, what I'm calling the phantom push. This paradox is hiding in plain sight in every ideal circuit diagram you've ever drawn or seen, and it really makes you question how current is even supposed to flow in the first place. Okay, here's the problem. For a current to actually flow, you need that push. You need an electric field running parallel to the wire. Let's call that Rule 1. But according to all the rules of ideal circuits, a simple connecting wire has the exact same electric potential everywhere along its length. That's Rule 2. You see the issue? These two fundamental rules are in a direct head-to-head conflict. And why is it a conflict? Well, it's because of a core law of physics. Electric potential has to drop in the direction of an electric field. It's just like gravity, right? A ball is only going to roll downhill if there's a change in height, a drop in potential energy. The exact same thing is true for electric charge. So, here's the knockout punch. If the potential along the wire is constant, like Rule 2 says it is, then the electric field along that wire has to be zero. There is no downhill. But if the push is zero, how on earth is there a current at all? It seems completely impossible. So the solution here isn't that physics is broken. It's that our ideal model of a circuit is, well, too perfect. It's incomplete. The real world is a lot more subtle, and the answer is hiding in a tiny detail that we usually just ignore. See, this paradox only exists in this imaginary world of perfect, zero-resistance wires. In reality, every single conductor, even something awesome like copper, has a tiny bit of resistance. And to push a current through that real-world resistance, you absolutely need a tiny potential difference, a tiny voltage drop. And this tiny real-world voltage drop is the whole key. It creates a very subtle electric field along the wire, a tiny gradient, you could say, or a lean. It's not some powerful shove, it's more like a gentle, continuous nudge, just enough to beat the wire's resistance and keep those charges drifting along. And this brings up another surprise. The electrons themselves are moving incredibly slow. Their average forward speed, their drift velocity, is often less than a millimeter per second. The energy from the field travels at almost the speed of light, but the particles themselves are just kind of shuffling along. This subtle push on super slow-moving particles, that's the reality of electric current. Okay, so we've figured out how the current gets nudged forward. But that just leads us to another really deep puzzle. Where, inside the wire, is this current actually flowing? This question actually started a huge debate among electricians and engineers, and the answer is even more surprising. And the argument was pretty fierce. You had one camp saying the current has to travel on the surface, which kind of makes sense for stranded wires with all that surface area. But then the other camp was insistent that it flows through the bulk, the interior of the wire. Both sides had what seemed like pretty logical arguments, but neither one was seeing the whole picture.
So who was right? Well, it turns out they both were, just in different situations. The real answer is decided by a single critical factor that completely changes how a current behaves inside a wire.
And that critical factor, it's frequency. Yeah, the behavior of the current changes dramatically depending on if it's a steady, one-way street or if it's flipping back and forth really fast. This is the key that unlocks that second paradox, and it has massive real-world implications.
All right, let's break this down. For direct current, or DC, the stuff from a battery, the flow is constant. It's always moving in one direction. But for alternating current, or AC, the stuff coming out of our wall sockets, the flow is constantly reversing itself, 50 or 60 times every single second. And that difference changes absolutely everything.
Okay, so for direct current, that steady flow is spread out through the entire bulk of the wire.
The current uses the whole cross-sectional area to get where it's going. And this means that stranded wire isn't really used to get better flow. It's just used because it's way more flexible than a big, thick, solid wire.
But with AC, something called the skin effect completely takes over. The alternating currents constantly changing magnetic field creates these little swirling currents inside the wire called eddy currents. And these eddy currents basically fight against the flow in the center and push the main current out toward the surface, or the skin, of the wire. And this isn't just some tiny theoretical effect. For the 50 or 60 Hz AC that's in our homes, the current is basically all concentrated within about 8 to 10 millimeters of the surface. So for any really thick power cable, the deep center of that wire is pretty much just dead weight, carrying almost no current at all. This is absolutely critical for designing things like high-frequency electronics and our power grid.
So, let's just recap the two big truths we've dug up today. First, that push that drives the current, it's actually a really subtle electric field gradient, and it only exists because of real-world resistance that we can't ignore. And second, where that current flows isn't a one-size-fits-all deal. For DC, it's through the whole thing, but for AC, it's all happening right on the skin.
And this all brings us to one last thought. That simple model of electricity we learned as kids is a useful story, but the reality is this beautiful dance of invisible fields and subtle effects. It really makes you wonder, if the energy powering your screen right now is this complex, what other fundamental forces and invisible fields are out there, shaping our world in ways we haven't even begun to imagine?